Next question is question 8. It says, Quan stands on the edge of the building's flat roof 12 meters above the ground and throws 147 gram, or I'll do 0.147 kilogram, baseball straight down. The ball hits the ground with a speed of 18 meters per second. So here we're going to have a velocity of 18 meters per second. What was the initial speed? Let's use conservation of energy because that's the unit we're in. So we need to think about energy before equaling energy after. Afterwards is the simple one because at the ground all it has is kinetic energy, 1/2 mv squared. So I'll just say kinetic energy here afterwards. Before it's got both kinetic and potential. So the kinetic energy to start with is 1/2 mv squared where we don't know the velocity. That's the velocity we're looking for. The potential is mgh equals the kinetic energy afterwards, which is mv final squared, and we do know that. So the mass is 0.147 times v squared, that's the v we're looking for, plus the mass is 0.147 times 9.8 times the height, which was 12 meters, equals 1/2 the mass, 0.147, times the final velocity, which was 18 meters per second squared. So if you write that equation and solve for v, that gives us the initial velocity that it must have had, 9.4 meters per second. Okay, the next one is question 9. It says, as shown below, a 450 kilogram roller coaster car starts from rest at point A. Let me draw this picture real quick. Okay, so it says that it rolls down the track reaching point B, and it has a speed at point B of 25 meters per second. And then it rolls back up the second hill and reaches a height of 23, so this height is going to be 23 meters above the ground. Before coming to a rest at point C, so it comes to a rest there. I'll put velocity equals 0 to remind myself of that. Question is, what is the gravitational potential energy and kinetic energy of the car when it's at points A, B, and C? So first point A, the kinetic energy, it says that it starts from rest, so that means it's 0. So it's got all potential energy at this point, and potential energy is just mgh, which is going to be the 450 times 9.8 times the height of 47 meters, which gives us 2.1 times 10 to the 5th joules. That's our point A. At point B, it's got just kinetic, so we can write potential energy equals 0, and then you can write kinetic energy equals 1/2 mv squared, so it's 1/2 450 times the velocity of 25 meters per second squared, and that should give us 1.4 times 10 to the 5th joules. And okay, then it says it comes to a rest at point C, so then we know that it's got all potential energy, again, mgh. So I'll put kinetic energy equals 0. Potential energy is going to be mgh, which we know is the mass of 450 times 9.8 times the height of 23, which gives us about 1 times 10 to the 5th. I mean, you get 101,430, but the book says 1.01 times 10 to the 5th, about the same thing. Joules. All right, the next problem is number 10. It says that Aaron holds a 1.2 kilogram bob of a pendulum at a level at which the gravitational potential energy is 3 joules. So we have a pendulum. I'm going to draw this, and I'm going to write right here that the potential energy is equal to 3 joules at that spot. Then we're going to release it. Question A says, predict the speed of the bob as it passes through the lowest point. So down here, we're going to reach the lowest point. We can figure that out with conservation of energy. So we know that the energy before has to be equal to the energy afterwards. So this is energy. Before we have all potential, so we have 3 joules of potential energy. I'll just write potential equals kinetic here because before we have all potential, and then at this point we have all kinetic at the bottom. If we called this our reference line, by the way, for gravitational potential energy, so we're calling that height 0 for our reference line. If we do that, then at this point we would have no potential and all kinetic, so we can write this equation. And then we can solve this. Potential energy is 3 joules. Kinetic energy is 1/2 mv squared, where we know that the mass of this thing is 1.2 kilograms. So I'll plug in 1.2 right here. and then I'll just solve for V right here. If you do that, you get 2.24 meters per second. Part B then says Aaron releases the ball from rest and uses a photo gate to measure its speed as it passes through the lowest point. She finds that the actual speed is 93.2% of the predicted value. How much work did frictional forces do on the pendulum? So we know work equals change in kinetic energy. So if we want to find the work, let's find out the kinetic energy. Well, we know that that would be 1/2 mv squared, which is 1/2 1.2 times this velocity that it has at the bottom actually, which is, they said, 93.2% of the predicted value. So I'm going to do 0.932 times the velocity we got in part A, 2.24. And that gives me the kinetic energy that it actually has at the bottom, which is 2.61 about joules. And I know that if I want to look at the energy lost, then I can compare it to the original energy of 3 joules. So it ended up at the bottom with an actual energy of 2.61. So if I take the 3 joules and subtract the 2.61, I get the actual amount of energy given off, which is 0.394 joules. So then part C says, by what percentage was the pendulum's original energy decreased due to the work done by frictional forces on the pendulum as it moved from the release point to its lowest point? The answer key has a negative here to represent that that's the amount of work given off. So we can make that negative. So let's compare the energy 2.61 that it actually has compared to what it started with, and we can see that we get about 0.87% or 87%. So that means that 13% of energy was given off. Next question, number 11, says a loaded freight car of mass 50 times 10 to the third, I'll just write this, 1, 2, 3, so 50,000 kilograms, is moving at the speed of 18 kilometers per hour along a straight and level track. It collides with a stationary empty freight car, and that freight car I'll call mass 2, has a mass of 15 times 10 to the 30 kilograms. The 2 boxcars lock together afterwards, and question A wants us to answer, what is the velocity of the moving pair of boxcars after the collision? We're going to use conservation of momentum for this, so we're going to say momentum before equals momentum after. Now I know you might be tempted to use kinetic energy, energy before equals energy after, but the problem is that we don't know if energy is given off. Momentum is always going to be conserved, so we can, when you have a collision, always use conservation of momentum, so that you don't run into that problem of not knowing if energy is given off. In fact, we might be able to answer that question. Yeah, and part B actually asks for that, how much energy is given off. So before we have one car is stationary, so all the momentum comes from the first car, which would be mass of the first one times velocity of the first one. There's no momentum coming from the second one. Afterwards, they lock together, so it's going to be mass 1 plus mass 2 times the velocity of both. So that's the equation we write for conservation of energy there. That would be 50,000 times the velocity of it, not 18, I'm sorry, we're going to have to convert this. So there's 3,600 seconds in an hour. So let's write 1 hour is equivalent to 3,600 seconds. And then also let's get rid of the kilometers, so 1,000 meters are in 1 kilometer. So we're going to have to multiply or divide by 3.6 in the end, which gives us 5 meters per second. So let's use 5 meters per second here. And that equals the mass of both of them added together, which is 50, so 65 times 10 to the third, or 65,000 kilograms times the velocity of both. So just divide by 65,000, and you get the velocity of both is about 3.85 meters per second. All right, part B then asks for how much energy is lost during the collision. So we can do energy before and find that and compare it to the energy afterwards. We know that these probably aren't equal because energy is probably given off in like heat and friction and the deformation of the freight cars. But energy before is all going to be kinetic energy from car 1, because we know that's the only one moving. The other one doesn't have any energy. Afterwards, we have the kinetic energy of both. So, and they're not going to be equal. So let's find out what they are. It's 1/2 mv squared for the first one, which is mass of the first one times velocity of the first one before. And let's compare that to 1/2 mass of both times the velocity of both afterwards. So the first one is 50,000 times the velocity of the first one beforehand, which was 5. And that's squared, sorry. It's squared. And that gives us 625,000 joules. And then if we do this one, it's 1/2 both, which was 65,000, times the velocity of both, which we got 3.85 squared. So if you do that and compare, you get 480,769.2 joules. And we can see the difference here. So originally we had this much energy. After the collision we had this much energy. If we just do a simple subtraction, we get the energy lost with 144,230 joule, 0.8, we'll say, joules. Okay, so 12 says an arrow with a mass of 320 grams, which is 0.320 kilograms, is shot straight up in the air and reaches a height of 150 meters before stopping and falling back to the ground. First question A, how much work is done by gravity as the arrow reaches its maximum height? So we know work equals force times distance, and it also equals a change in kinetic energy. So those are the tools that we have to use. We could use kinetic energy, but we have to find the velocity, so let's just use force times distance. The force that we're overcoming is mg, and the distance that it goes is the height. So the mass is 0.320. The force that we're gravity is 9.8, and the height that it goes is 150. That gives us 470.4 joules. And technically that's the work done by gravity on, we'll call that negative then, since that's the work done by gravity on the arrow. But I won't mark you wrong for that negative sign. That's just the work that gravity does to slow the arrow down. Okay, for part B then it says, if the arrow's kinetic energy is 0 at its maximum height, calculate the initial velocity this arrow was shot from the ground. So if we do the energy before is equal to energy afterwards, then so we're neglecting air resistance and the energy that's given off through air resistance, obviously. So we can do conservation of energy here. So the energy before is has to be 470.4 because that's basically how much energy gravity stores up in this thing, essentially. So if we do that, we now know the energy before is 470.4. So we can set that equal to the formula for kinetic energy, 1/2 mv squared, and we can solve for that velocity, where the mass is 0.32, and we can solve for velocity. 54.22 meters per second. All right, so then 13 says the nucleus of a single atom of uranium, U-235, consists of 92 protons and 143 neutrons. How much potential energy is contained with just a single uranium nucleus? So we know that this is the mass of both a proton and a neutron. So if there's 92 protons and there's 143 neutrons, then we know there's 235 particles together times the mass of each of these, which is 1.67 times 10 to the negative 27, gives us the mass that's there total in the nucleus. And then from there we can use E equals mc squared, where we use that mass that's there in the nucleus times the speed of light squared. The speed of light is 3 times 10 to the 8th meters per second. So we're going to want to square that. And then that gives us the total energy in joules, which is, this is 3.92 times 10 to the negative 25th. And then when you do the multiplication, you get 3.53 about times 10 to the negative 8 joules of energy. So this might not seem like a lot of energy, but obviously this is the energy that's in one atom. So you can imagine trillions of atoms in your body. There's a ton of energy in matter. Okay, I hope this helps.